assets have different Sharpe ratios, how could a single discount factor, a single random variable and work and give you expected value of plot zero? And, you know what I mean? If that,
there's more. It's actually
between two assets. You know what I mean?
Yeah, and then also the discount factor is actually represented by the tangency portfolio. So it gets funkier. But that's like standard. Like if you know Cochrane, the asset pricing book, that's what it's all about. It's all that's what the whole book is.
Ask them if they're good. Ask them if they can see.
Yeah, it's a little mind-blowing. It's a little. It's an interesting way to look at it. This is also the other papers also mention it, you know. But this is what's new is really that this kind of take. Continue here or
yes, we're good.
Okay. Let me get back to the picture. Okay, so we're talking about how the stochastic discount factor here actually comes about. Usually, you have the equation here where this is a future payoff, and this would be the price. But if you express it in return terms, then you know just more seconds. The point is that this implies a one-factor model, where what you want is to estimate this quantity. And then you can express this quantity as a function of the tangency portfolio. But let's take a look at what we get to the model in a second. Just briefly what generative adversarial networks are, because we need them for the model. So these models are also called GANs, right, as the acronym. They have been called by Jan LeCun, who's like the fanciest kind of CNN inventor at Facebook, this exciting idea in deep learning in the last decade. You see here is what AI really needs to do is learn stuff from scratch and learn how things really work. So adversarial networks has two terms in it. So it's generative and it's adversarial. It's generative because it really learns how to create something from scratch. And then it does that in a way that's adversarial. So two networks play against each other. There's a setup where you have these two networks that play a zero-sum game against each other. And it's commonly used, and you must have seen these artificial generator, right? Celebrities that look like real people, but they're not, and so forth. And the way this works is that you have two networks. One is a generator, one is a discriminator. And what's interesting is that the generator literally gets fed random noise. And then from that random noise is supposed to, and very often does, in fact, learn how to produce an actual image such that the discriminator, which sort of randomly sees either an actual image, you know, from the class of data that it's supposed to learn, you know, the ensemble is supposed to learn, and the output of the generator. And this is successful when the discriminator is no longer really able to make, you know, a successful decision between right and wrong. So
what's the ground truth? I mean, it sounds like you got noise on both sides.
This is the ground truth, right? So this would be so say you have, I think these celebrity images came about because there was a data set that had a lot of celebrities in them. So that's the ground truth. You pick the ground truth. You say this is the class of objects that I want the network to learn. Be that financial data, could be a time series of, you know, stock returns, or it could be images of skyscrapers in New York, or whatever. And then these get fed in on the one hand. On the other hand, you get fed a data object of the same dimension that contains random noise. And what's really fascinating is that these models then actually learn to produce something that looks like these examples. Really, if it's an image, then as a human, you are no longer able to distinguish them.
Yeah, I was at the Sotheby's auction when they did the Montreal. I'm sure you know about that, right? Like the first piece of
you get
art.
And you can you can do like style trade. You can do all sorts of things, generate all sorts of things. So it gets very creative, and people were very excited about this. And there's a guy who invented this while PhD intern at Google. Yes. Yeah, it's the exact same. Yeah. So you produce fake data that is generated. So it learns distribution of an image, for instance, look like. What is the distribution of a celebrity image? It comes, of course, with all these problems of fairness, and then you have a bias in data, and then so there's a whole, you know, discussion on that. But
finance, what's the obvious, you know? Would you try to recognize head and shoulders? Like, what is the obvious application?
So you could do that. So in the book there's a new model that came out 2 years ago by a guy at Google. It's called TimeGAN, where the idea is you synthesize data. And that comes out of the medical domain originally. So there was a model developed in Switzerland. Have you seen this, or you're nodding? So there's a model coming out of the medical domain. But obviously it's hard to get numbers of medical data because of privacy and whatnot. So they wanted to build an early warning system using patient data from an intensive care unit. So they only got like whatever 10,000 samples, not enough. So they thought maybe we can synthesize another unlimited number of data points, and then we have a lot of training data. And they managed to build a model that synthesized short time series, like observations every 5 minutes or whatever. You're in the intensive care units, hooked up to all these machines, and they take measurements. So they were able to synthesize data that you could train a model on these synthetic data, and it was successful predicting data. So now, of course, you could try to generate price data or return data in economics. So that model does that, and there's an implementation in the book that shows it does work at small scale. So it's surprisingly good if you only do like 24 observations and daily stock data and things like that. You can actually build a model on that works. As soon as you scale it up, it gets a little hairy. But the interesting part is that this years to get right in deep learning, right? So these images that you see today, they look nothing like this when this they looked actually pretty crappy. But after 4 or 5 years and hundreds of papers written about this, suddenly you have really good models. So maybe this will find us as well. So we'll see.
Well, what really happened? What do you think in your opinion? I mean, I was trying to do this stuff in the early 90s, which was the AI culture, and we were, for temporary expert systems.
Yeah.
Why do you think it suddenly is so good, like between 2013 and now? Like, what's the big difference? We train a lot of copy bots, and
I mean, what changed is more data, more compute, right? These things evolve in lockstep, right? I mean, suddenly you have YouTube, right? I mean, you get all these images, you get videos en masse, and suddenly, to inputs, you have an unlimited supply if you are Google. It's not a surprise that this was developed at Google.
That's true. I mean, like with social media, you kind of do have unlimited input because the user is supplying so much data now.
that explains. And that explains a good reason why this worked. Together with people, I think, sticking to their guns, like the folks that won. So deep neural networks, deep learning, came on the map in this 2013 ImageNet competition, where for the first time the deep neural convolutional network won, right? And it was like a student of George Hinton who had been at this since the 80s. And just like Jan LeCun, these people were considered weirdos or outsiders, at least, in the 80s or 90s, when everybody else thought this is doomed to fail, and they were just keeping at it, and look, now it's pretty good. So that changed. So that's GANs in the wild. So
let's hope it doesn't happen in finance too soon.
Think Google starts a hedge fund?
Well, you know what I'm saying. I mean, it could be disrupted. So
it certainly could.
How do you account for the inevitable volatility that just occurs on almost a random basis?
If you want to generate synthetic financial data?
Yeah. No. Predict some price within 30 days in the future.
Yeah, there will be some mistakes, but then the other cases where you don't make mistakes. But then also, you have the fact that volatility is often...
What if you combine a volatility model with what you're doing here? And if you had a low vol environment, discriminate between low,
absolutely,
mid-range, and high, which we have that. So we run that sort of model. We see that we're in the low volatility regime now. So if we were to take some sort of, do something like this, there might be some predictive value in figuring out what will be 30 days in the future.
Yeah.
But what happens if there's an increase in the VIX and there's an increase in the vol regime, switch from a low to elevated or a high vol environment? We know that all bets are off.
So if you look at modern machine learning systems, the way they run, done, not necessarily in the finance industry, but generally. They rarely, this is our one little model, and that's the one thing we kind of cater to and like, you know, put water on. And they're usually a combination of a bunch of different models that have different functions, and they all work together. Now, clearly, to build a system that works in the market, you might want to get different decisions that you would be taking as a portfolio. You would want to get inputs for those from different models that are specialized for tasks. Absolutely. Yeah. Now, these examples, they're typically focused on one task, just, I mean, right, for illustration purposes. Now, if you build a system, that's a different story. Good. So this is GANs, like, generally speaking. Back to the finance model.
With this synthetic data, I'm just curious.
Yes.
You know, like simulate stuff, right? You can always run Monte Carlo or something. If you just want to, like, what is so about generating this type of GAN based?
Well, the question is how good is it? And the ultimate test is that you can use fake data to train succeeds on actual data, as good as a model trained on real data. The synthetic data that I see generated by other, you know, random like simulations and the like, they don't standard. The GAN data that are being generated today, some good examples. There's like more modern GANs, like a Wasserstein GAN, a Core GAN, and things like this. They work a little bit, but they're not there yet. Because finance, for the very phenomena that we always talk about, like the fat tails and peculiar, and the low signal content, these synthetic data, they don't cut it. You know,
it's one thing to, you know, train a neural network on recognizing the road and reading the lines.
Yeah. No question.
It's pretty simple compared to driving the desert, and then finance is more like driving the desert without a GPS. You don't know north or south. You don't know markets at top or bottom.
Yeah. So you see that for some tasks, like these asset pricing examples, the models start to actually deliver some value. They don't hit it out of the park, but clearly there's some value there. If it comes to generating synthetic data that looks like real, I'm sure that many large institutions are working on that because it could work, but it doesn't yet. At least it hasn't been demonstrated. It's hard.
I mean, the real challenge is, you know, if it's, stuff is so non-stationary that, like, what do you imagine?
Yeah, the challenges are pretty clear, and it might never work, you know? But then also, you got surprised. You would not have predicted that image data can be synthesized so easily. Once you know it after the fact, well, it's kind of obvious, you know, but who knows, you know? People will come up with solutions.
To me, it's still not obvious.
Yeah, no, it's hard.
Please.
It's also really, so these GANs, just as a side note, they're really, really hard to get right? So the outputs look amazing, but in practice, this is about an equilibrium between two networks. I mean, you can imagine how easily you can end up in an equilibrium that is bad, where, for instance, a generator just produces something very narrow, right? Very simple, like it's highly realistic, but it's just that one kind of example that the discriminator of things works. It's, you know, so you can have bad equilibria that don't cover the entire domain of the distribution. So to get that actually right is far from straightforward. That's why people have worked on this for years. Good. So back to deep learning and finance. So the interesting part about using this generative adversarial network, that if you had asked me a year ago, like I would not have been able to finance beyond synthetic data. So this actually builds on a paper by Jansen and Jansen. I don't know how to pronounce this right. So this guy in 1997, they showed that first of all, if you maximize the largest pricing error, so if you minimize the largest pricing error, then you are able to find the stochastic distance that is closest to one that is permissible given the restrictions that we have about that factor. So that already looks like a minimax solution. They explored that minimax kind of as a game theoretic approach could actually work. So some smart PhD student, the guy who's now at 2 Sigma, he happened to be at NVIDIA an internship before, where it's all about images and GANs, that you could maybe combine these two things. So what they did, let's use a general method of moments approach to estimate the stochastic discount factor using instruments, right? Formulation where we use again something that uses information from a large number of characteristics to come up with synthetic test portfolio that the model is then supposed to price correctly. And it does that in a way that you iteratively, I mean, I talked about the training method, but first of all, to be able to price it unconditionally. And then you come up with instruments that throw the model off as much as possible and then force it to relearn its business. And that works then surprisingly well across all actual assets. So that's basically what the approach is. So let's look at the model on the next slide. I think the architecture may clarify this. So this is a significantly more complicated model that starts to look more like modern sort of deep learning networks. So you have supposed to estimate these stochastic discount factor weights, and one that ends up with instruments. This was the conditional moment equation that I showed on the before, where the goal is to minimize pricing error. So these tries to price assets correctly using these synthetic tests that are generated by this network, and the weights to do that, which here produce our stochastic discount factor, they are learned over here. You get in a large number of inputs, so you have, I don't know if they can still hear me. So you have macro features and you have asset features that come in. So as before, you have asset characteristics like your typical momentum, etc. aspects, size and so forth that go into the model. And then you have macro features. And these macro features were novel in the sense that there were so many of them. So we have 107, there was a paper that mentioned like 160 or so different time series that potentially could help predict asset prices. So they built a neural network, a recurrent neural network that condenses these 178 series that are in time, basically compresses it to a 4-dimensional time series, right? So typical, we call it embedding or like a compression. But the compression is learned together with the rest of the network, all of this to minimize the pricing error. So it's not like a sort of unconditional compression where we just try to kind of reduce information so that we lose as little as possible, or we try to condense it in a way so that it is most useful to help us predict the information or to produce useful features. And these are different compression networks. They actually have different number of states. So this only compresses it to 32 states. So you have different macro on each side, and they provide an input to a feed-forward network where we have our features, and on the one side we predict these weights, and on the other side we predict the instruments. And then together in an iterative training process, we optimize the asset pricing errors. That's number one, and then we're not done yet because we have to do something with the results to actually loadings, right? So this helps us to predict the weights of constitute the this stochastic discount factor. Then we still need to figure out what is actually the exposure of each asset to that factor, and that's on the next slide. So on the next slide, you'll see that now we can create. So we want this factor model, right? We get this f plus 1, our ft plus 1, our stochastic discount factor. We get this out of the first network, the GAN network. Now we need the betas. So we can come up with this proxy beta because beta depends or is proportional to the product of the returns and the stochastic discount. So we have a proxy for beta that we can use to train a neural network to predict it, so that then at predict time, we can actually use our weights to come up with the results. So we can actually predict the asset. You can use the asset characteristics to predict to the factor which we get from the other model. So we have these two models that play together that give us both the stochastic discount factor and the individual asset sensitivities or loadings. So look at that. That was probably a lot. So questions? I know it's getting later, and seen the drinks have been. Are you guys following me? Yeah. Okay. Good. So this is a model that kind of comes up with this factor model estimation, and this works remarkably well. So if we look at the next slide, then so here you see the training. So the authors made some code available, like in an old implementation, supported it to TensorFlow 2, and you can see how the Sharpe ratio of this stochastic discount factor portfolio, so using the weights that we estimate, that the sharp ratio improves actually quite a bit on the test set, as we train this for some 12,000 iterations, repeating this iterative sort of GAN, this adversarial game, several times, right? So this gives us weights that produce an attractive sharp ratio. In addition, the authors use an ensemble, so they actually train this whole thing like 10 times and then average the results, which further boosts the output. And they basically follow this 3-step training procedure. So that's
ensemble is a one template.
so an ensemble is just like you have several models and then you average or combine the results. Right?
Well, what are those templates?
The same, they're identical. They're the same model you just train. So the point with neural network is that random initialization, you may end up in a very different spot. So to protect against the variance that results from this randomness, typically you train multiple of them and then you average the results so you have less of that.
Ensembling on the initial point.
Yes.
Okay.
Yeah, it's just a random,
I got it.
you know.
But that's different than when you have an ensemble of learners where the individual learners are sort of like,
Sort of. I mean, the typical boosting type of idea is slightly different, where they have to be trained. These can be run in parallel. They're completely independent of each other. But you have all sorts of ensembles. If you look at a Kaggle competition, people just bundle together all sorts of stuff, as long as it improves the output. But yeah, in this case, it's an assembling just like it's a regularization approach to reduce the variance.
Stefan, on the y-axis, I can't read those numbers.
Here's sharp ratio on the test.
Yeah,
It's the monthly.
what kind of ratio?
This, I think this is 0.1. So there should be something like 0.67 here.
I'm sorry, how much?
0.6 or 0.7,
Okay.
something like that. 1, 2, 3, 4, 5.
0.7.
It could be 5.
My investors would not be impressed.
Yes, 0.6.
It's 0.6? Okay, thank you. So it's 0.6.
0.6?
Yeah, this is 0.6.
Okay.
But it's monthly,
Yeah.
and no.
oh, so that would make a big difference.
So you get
So
the
what would make the difference?
You say it's monthly, so if you do a root of 12, then
Oh, it's a monthly
it's
chart?
monthly, yeah. Oh no, it's interesting. I mean, I wouldn't be standing here if.
So what's the annualized number? I'm not as smart as you guys.
So that's the monthly sharp ratio annualized on trained test. No, sorry, it's not annualized. It's not annualized. So this is times square root of 12, which is something like 3 point something. So it's around 2.5.
Okay, now we're talking.
Right? And that's the test set, right? So this uses 20 years of training data, something like 57 to 77, or no, 67 to 87, then 5 years validation, figure out what the best model is, and then a test set 30 years after that. Right? So something like that, maybe 25, 30. So
You're rebalancing monthly, right? You're rebalancing the portfolio.
yes, yes. Yeah. This is the result for the estimated, it's based on the estimated weights, which are estimated on a monthly basis. Again, this is not a strategy that's being implemented with the transaction cost, and of course the turnover would be massive and whatnot.
Right.
But so this is not like, oh, this is a strategy we can run tomorrow. This is about how good is the estimation of the tangency portfolio by
Right, I get that.
You know what the turnover like?
Right.
Any idea what the turnover is?
There are numbers in the paper, I don't know if them it's high. It's high. But still, I mean, the pure, if you just take the returns at face value, they're like insane. I mean, so something you can't quite.
Yeah, I'm sorry, you probably touched on this an hour ago, but what are the assets you're testing?
US, all stocks available in the CRSP database. In this case, and that's the data set that's available online, they only use, it's US equity. US equity monthly data since the 60s, they only use stocks that have all the characteristics available. So whereas the other models sometimes use data that has just whatever, if you have missing data, we're just going to put in the median. This model only uses data or stocks where for a given period, all the covariates are available. So the assets.
So that's the CRSP.
Yeah.
Data set.
So Let's keep plowing ahead so that
Yes, I know.
because we do have some food, guys. Just,
And there's Austin as
something
well,
to
I
look forward
wanna-
to. And then we'll do like a very short break so you can get some food, and then we'll plow ahead with the next speaker in the interest of time.
We're almost done. It's like 2 slides.
Only 2 slides?
Yes.
Oh,
Can we do that?
yeah, of course.
Okay. So now there's a critical paper that by chance reviewed all of, or not so much by chance because these I think are the most outstanding papers. And recently it's by Abramov and other folks. And the idea was like, but if we actually look at the stocks in the sample and whether we could trade them, what's actually the economic value of it? If we impose all the economic, that's why it's called machine learning versus economic restrictions. If we look at the reality of actually trade, what happens? So, and then, they exclude, basically they take the model, they build the models, take the sample, and then eliminate stocks that, fall under microcaps and so forth. And also looking at turnover. So in that paper, there's a lot of detail on what the turnover looks like. And then you see quite a bit of a drop. So this is the monthly returns. Yeah, these are the monthly returns based off of these different models, right? These are the 3 models we just reviewed. The first one and the other. And if we adjust using Pharma French 6, and then the discount, so the drop in performance in percentage points, if one of these conditions applies. So of course, now interestingly, the GAN model actually responds to that, and they updated their paper, and they said when Avramov built their model, they used to generate the predictions. So instead of the bit, so what you want to use if you use the GAN model to pick the top and the bottom deciles, you want to use the betas, right? The exposure to the factor, not the stochastic discount factor weights. And they did the second. So the portfolios that they use to come up with their conclusion are not the ones they should have been using. And in their analysis, in the GAN paper, it does not make a big difference if you eliminate those steps. It does make a difference, for sure, not as dramatic as this. But that's hope.
How do we do numbers like in the kitchen sink? If you have decile spreads, monthly spreads are 156 beeps, that goes down to 92 beeps. If you adjust for Pharma French 6, or I don't know what that means.
So this is the returns that are left after the residuals of Pharma French.
Okay, and then when you say no microcap, 66% means that 2/3 of the 92 beats goes away if you take out microcaps. What if you take out all 3? If you take out microcap, spread, trading, and distress?
I don't know off the top of my head, but there are tables on page something
Okay. It looks like there's nothing left. I mean, it's
So-
very little.
Yeah, but then the question, exactly, right? So, and that's what the discussion is a little bit right now. How do you account for that? Do you build models that factor in, these and so forth?
No, it's totally. I mean, that's the honest answer is that most of it's Moroccan, and the people who are actually.
The discount factor of 66% means the returns are down by 32%.
No, it's down by 66%.
It's down by 66%.
So to the extent that here, in this case here, none of the models, I think, generate like any meaningful success. Yeah.
So the last number is 94%, means you're only left with 6% of the original number.
Yeah. So nothing in excess of what the Pharma French can account for.
Right. But what do you mean by distress discount? What is a distress discount?
So distressed assets they have the definition in the paper. So there are no credit risk. It's like no credit risk and rate, or like a deterioration in the credit risk rating over a certain period. That is derived from some of the characteristics in terms of what they're.
I mean, it's a valid source of risk premium. I mean, like microcaps, you can argue that it costs nothing left, you can't trade it, but
You might include, yeah, exactly.
you could say that, you're earning a risk premium for
course.
your risk or whatever. You chose to take that.
Yeah.
A lot of people, some people do in private equity.
But some big institutions might have risk mandates.
But very interesting stuff. Let me just ask you one really silly question because, I always sort of get stuck on this whole issue. Like you brought so many cool results to the table, which most of us who don't know that much about machine learning, certainly I think a lot of people, some of this stuff has been done in finance here, right? Or deep learning for that matter, although I'm not sure if when you talk about layered neural net, is that really deep learning, or is it determined by the number of parameters, number of layers?
Technically it is, but you gotta admit, if they have 100 billion parameters and this has 5,000, what use is there in applying?
Well, that's what I mean. So that's a silly sort of question about, maybe you can call it taxonomy but I remember in '94 when we were doing 3-layer networks to do the first driverless car with that was not the same as what you're doing today with 3 layers. But
it was certainly harder to implement back in the day.
True. But what I'm actually more confused about is, I think there's context shifting between Follow and Bev, and you keep talking about explaining the variance, but also predicting sort of out-sample returns in the sense of form of range. So those are two very different things.
Yes.
You can either have a risk model that explains cross-sector variance, or you can return model that tries to predict.
And you gotta pay very close attention. And I could leave this as a riddle. There's one model there that actually does not predict. So it only uses contemporaneous returns as inputs and outputs. But other models do predict. So first the kitchen thing and the GAN models, they both actually predict. So you can work with them not knowing future returns and get future returns predicted. You can of course also use them to explain concurrent returns. But the autoencoder model uses contemporaneous inputs and as outputs. So that doesn't really predict anything. You can use it out of sample in the sense that the model is estimated beforehand, but it only does explain returns as you observe them, which is of course different. So that's a very good point.
It's a lot about LSTM model, right? Like, would you still say that it's only for all ML research? I mean, it seems like there's been a lot of work with LSTM.
That they're critical of them, that don't work, or?
So I'm asking you, like,
Sorry.
would you still think it's early days of finance?
So I think, for instance, it's interesting actually that the time GAN model that I mentioned about the synthetic data and this model, they both use recurrent neural network to condense time series. That is a very useful application, right? So not necessarily a recurrent neural network to something, but if you have a lot of time series data as inputs, to find a useful representation that has much lower functionality, a recurrent neural network is a good way to go about this, Very often you have to kind of learn how to use the tools the right way, It's not everything like return is always the output and whatever you have is the input, and then basically you run through scikit-learn and like swap out that you have until you find something. So it's often much more in practice, such as predicting regimes on the one hand, and have another model that
I mean, you need a lot of.
So that's actually the main takeaway, right? So as you see these models evolve, and the authors stress that, and it's obvious that to build these models so that they're actually successful, you have to design them in the way that they incorporate prior knowledge, right? I mean, that's like the basic idea of machine learning. Unless you generally are able to know something, a model will never be able to predict anything.
Fantastic. Well, Stefan, big round of applause. Definitely one of the better talks I've heard in recent times. And how many chapters do you have in the book? Of course. How many chapters do you have?
Sorry?
How many chapters do
The
you
book
have?
has 24 chapters.
Wow. Okay. And this was only one chapter?
It was around one chapter.
Okay, excellent. So we can have you back for a few more. Okay. All right, you got a wealth of material there. Excellent. Folks, why don't we break for a few minutes? Some food there, so let's help ourselves. Take a little bathroom break, and we'll reassemble hopefully in 10 minutes. It's almost 8 o'clock. So let's try to regroup in 10, 15 minutes and get started because we're a little behind schedule. But hey, we're here to have fun, so who cares? And then hopefully we can start again soon before Austin leaves. Our in California online, so I'm just trying to make sure Austin doesn't leave. I mean, we don't have him as well fed and watered as you guys. My apologies.
Nice to see you.
We're 2 or 3.